Welcome to EGME-333 Fluid Mechanics. In this video, we're going to discuss the topic of boundary layers. To begin our conversation, let's first observe what happens as viscous flow travels over a flat plate. From the video, what we observe is that once the flow interacts with the leading edge of the flat plate, the fluid in direct contact with the leading edge of the flat plate, its velocity goes to zero. As the flow continues to propagate further and further downstream, the flow near the surface of the flat plate experiences a slower velocity than the fluid further away from the flat plate. As the flow propagates downstream, the fluid that is further away in the vertical direction from the surface of the flat plate experiences a higher velocity than the fluid that is closer to the surface of the flat plate. So to understand this, let's further analyze the viscous flow over a flat plate. To do so, we'll track the position of a set of fluid elements. We'll have fluid element A in red, fluid element B in green, fluid element C in blue, and fluid element D in orange. And initially, we're going to place all of the fluid elements in the same axial position, which will correspond to time equals 0, and they are at the x equals 0, the leading edge of the flat plate. However, each individual fluid element is going to be in a different vertical y position. So at different instances in time, these fluid elements will propagate downstream with the free stream. However, due to their vertical position, the further away a fluid element is from y equals 0, the more it travels in the x direction. Consequently, the position or the distance that each fluid element travels is equal to or given to us by its local velocity in the x direction little u times delta t, the time that has elapsed. Given that the position in the y affected the local velocity, we can argue that the velocity in the x direction little u is also a function of y, where the velocity in the x direction increases with y. Let's revisit this viscous flow over a flat plate. But instead, what I want to consider is not so much the position of each fluid element, but rather the deformation that a fluid element may experience within this flow. So I'll consider two different axial positions, x1 and x2. And locally, I'll sketch out their corresponding velocity profiles as shown here, so we can zoom in on position x sub 1 and here at position x sub 2. We'll note that in both cases, they do have a velocity profile where the velocity in the x direction increases with the vertical position y, but the rate of increase is different in both cases. So the velocity profile does change with both x and y. It's not simply a function of y for the entire flow field. So let's focus now on the deformation of the fluid elements. Here we had 4 different fluid elements that we were considering, but let's focus on specifically fluid element D at time equal delta T1. So if we zoom in, let's assume that this fluid element initially has a square shape. Now, due to the variation in the flow field, this fluid element will experience some form of shear stress. Similarly, at some time later, this fluid element will still continue to experience some form of shear stress. However, what we may observe is that this fluid element will experience a very small level of deformation, which arguably will correspond to the local velocity profile or the local shear strain rate du dy being close to 0. On the other hand, if we focus on a fluid element B, which is closer to the surface, again, initially we'll assume that this fluid element had the shape of a perfect square. However, due to its close proximity to the wall, it's going to experience a higher level of shear stress. This will result in a higher level of deformation. So it experiences a shear strain rate, du dy, that is not negligible. So if we consider the flow behavior at different times or at different stages within the flow, we can identify points where locally the fluid element will transition from experiencing a negligible amount of shear strain rate to a non-negligible amount, which we can label here with this X. If we connect these X's with a line, then we can isolate the fluid into two separate regions, where the region close to the surface, we call that the viscous region, and the region outside, we can treat it as an inviscid region, where the fluid outside of the viscous region behaves inviscidly. And it's not because the viscosity is actually mathematically equal to 0, we just model it that way, but rather that the flow experiences an insignificant amount of shear strain rate, or that the shear strain rate is negligible. And the boundary that separates these two regions in the flow is what we often refer to as the boundary layer. To better visualize the growth of this boundary layer thickness, let's consider the opposite situation, where instead we have a static fluid and we have a boundary that moves, so that we can see the introduction, or really the influence of the boundary motion, how it affects the local flow. So we'll compare two cases, where the case on the left-hand side has the viscosity 10 times higher than the case on the right-hand side. So if we compare both cases, the case where the viscosity is higher, the left-hand side, the influence of the motion of the boundary penetrates the flow or diffuses into the flow faster than the case where the viscosity is 10 times less. So we can say that the fluid with a higher viscosity diffuses the disturbance faster into the flow. Or if we think about it in terms of a boundary layer, flows with higher levels of viscosity or lower Reynolds numbers will grow the boundary layer faster than flows with higher Reynolds numbers.